yours.
Okay, thank you. Yeah, so this is Shufang, and the presentation is about synthesis with the mandatory stop actions. And the joint work with Giuseppe, Giacomo, Antonio Di Stasio, and Giuseppe Perelli, and we are all from Sapienza University of Rome. So thanks for the introduction just given by the basic introduction of this work given by Professor Giacomo. So this work, we studied a similar scenario. It's synthesis under environment assumptions, where we want to automatically synthesize an agent strategy with respect to a priori knowledge of how the environment works. So here, this is a model of a reactive system where the agent interacts continuously with the environment. In particular, here we specify the agent task in linear temporal logic over finite traces, for which we can use to capture agent tasks over finite horizons. But the environment specification is given in LTL. And the goal for solving this problem is to obtain an agent strategy, which is a function that reads any past history of the environment behaviors and returns a proper agent action, such that for all of the environment strategies that enforce the environment specification, and on the combined play, we can find a finite prefix that satisfies agent task. So intuitively, the agent task describes the desired goal or task when the environment behaves as its specification. So the main challenge of this problem actually comes from the environment specification because it is specified in LTL. And for handling which we very often have to deal with the Buki determinization, which has been shown to be intractable in practice. And there has been a lot of attempts try to solve this problem. For example, having some restrictions on the form of the specification in LTL. For example, we can either only deal with safe LTL or co-safe LTL. However, for all these instances, with the specification still has to contribute to the gamma arena construction, for which we don't want it to happen. And another attempt towards focusing only on simple fairness or stability, or even GR1 fragment, which is a generalization of fairness. However, in this case, we still have some restrictions on the expressiveness on the environment specification. In this work, we study the synthesis with mandatory stop actions. Instead of having restrictions on the environment specification, we introduce a fundamental requirement on the agent strategy, which is that the environment has to play or perform a mandatory stop action. This stop action means that the agent cannot do anything anymore, which means that since the moment of playing stop, it has to play stop forever. So let's look at this example of a shared kitchen to see what a mandatory stop action means. Given this agent task of cleaning the dishes, the environment specification says that, okay, eventually someone else is gonna do the dishes. And now let's look at this this agent strategy of wait until someone else does the dishes. Well, this is a very lazy strategy. So if there is no mandatory stop action, actually this is a winning strategy because the agent just keeps waiting until someone else does the dishes. However, with mandatory stop action, this is not a winning strategy anymore because the environment can perform as the follows. It cleans the dishes after the agent stops. And now in this case, actually the agent task of cleaning dishes cannot be achieved when the agent stops because the environment can always start the dishes after the stop action. So the impacts of having this mandatory stop action is as follows. So the agent cannot wait until the environment brings some favorable conditions, and instead it has to aggressively achieve its goal. The key idea for solving this problem comes from the following observation. So every LTL formula can be considered as a form of a combination of safety part and the liveness part. If we look into them individually, so the safety part means that bad things never happen, which means that the environment has to maintain in a safety area for any finite prefix. It doesn't matter when the stop action is performed. So the agent can exploit this environment safety to achieve its task. And now let's add back the liveness part, which says that good things eventually happen. So besides maintaining safety, the environment still has to satisfy its liveness in the future. But actually, this liveness can be satisfied after the stop action is performed because of this eventually property. This means that the agent cannot exploit this liveness to achieve its goal. And then we have this key result. So for the case of considering agent mandatory stop actions, we can actually discard this liveness part coming from the environment specification, and for which we have this important theorem. So given a synthesis problem with mandatory stop actions and agent strategy, so this agent strategy is a winning strategy for the original synthesis problem if and only if it is a winning strategy for the reduced problem where we only consider the safety part. So for solving this problem, the key step is abstracting the safety part from the given environment specification. So actually, we can just build the non-deterministic bookie of the specification and mark all of the states as accepting states. And we can even determinize it by subset construction instead of having complicated bookie determinization. And now we have this reduced problem. And we want to solve it by having an agent strategy such that allows the agent to achieve its task when the environment behaves such that maintaining the environment safety. Notice that now we only have the safety part. So this can be solved as follows. We restrict the environment to its safe region through solving a safety game. And then we can build a deterministic automaton that recognizes the agent task. And the final step is combining these automata, and then we just solve a reachability game. And it should be noted that in this complete procedure, there's no step that involves bookie determinization. So the second part of our work is, okay, now we're not satisfied with just having agent task. We want to have agents safety requirement. Now the goal is enriched, and it consists of the task and the safety, agent safety. So this requires agent to achieve its task before the stop action, and also has to maintain the agent safety over the entire play, which is actually infinite, even after the agent plays the stop action. So now we need to notice that actually since the stop action is played, maintaining the agent safety property has to only rely on the environment because the agent can only play the stop action. And the key idea for solving this enriched problem is that we consider the game into two phases. The phase one is before playing the stop action. And now we have a finite prefix that satisfies the task and not violating the agent safety. And phase two starts from since the first moment of playing the stop action. Now we have an infinite suffix that only has to maintain the agent safety. And the agent needs to guarantee that when going from phase one to phase two, and it needs to make sure that playing stop action in phase two is enough to prevent the environment from violating the agent safety. In this case, actually, we need to have this set of non-stop states that mark the moment from which if the agent only plays stop action, the environment is able to satisfy the environment specification by violating the agent safety. So actually we can build a non-deterministic bookie automaton recognizing the environment specification and the deterministic automaton that recognizes the agent safety. Then we can construct the product automaton, and on which we can just conduct model checking techniques to collect this set of states from where if the agent starts playing stop actions forever, and then the environment specification can hold, but the agent safety can be violated. And on this, we can obtain this set of 9 stop states by projecting the C to the states on the agent safety automaton. And after having this set of 9 stop states in hand, we can now synthesize an agent strategy that allows the agent to achieve its task. But at the moment of achieving the task, it has to avoid these 9 stop states. And also later, when the environment maintains the environment safety. So first, we again restrict the environment to its environment safe region. And then we build the deterministic automaton recognizing the agent task. Then we combine these 3 together and then solve a reachability game. In particular, the goal of this reachability game is we have to reach the accepting states of the agent task automaton. But the moment of reaching it, we have to avoid these non-stop states. And along the way of reaching it, we can only visit the safe region of the agent safety and also the environment safety. Again, that in this complete procedure, there's no step that involves the bookie determinization. In conclusion, in this work, we studied the problem of synthesis with mandatory stop actions, for which we don't apply any restrictions on the environment specification, but we have this mandatory agent stop action that is applied on the agent. And we showed that in this scenario, we can set step the bookie determinization associated to handling the environment specification, which is given in LTL. In both of the scenarios, either we only have the agent task, or we also have the agent task and the agent safety. And I think this concludes my presentation, and